Alright guys, continuing the video, we found that we were given the 0.22 moles of the phosphoric acid here, and then we had 1.45 grams of the calcium hydroxide here. We converted the grams of the calcium hydroxide into moles of calcium hydroxide using the molar mass. 74 grams for every 1 mole of calcium hydroxide, giving us 1.96 times 10 to the negative 4 moles of calcium hydroxide. Which reactant now will be the limiting reactant, and which will be the excess reactant? We're going to show our work using dimensional analysis. So first we take the moles of the one reactant. So if we have 0.0222 moles of phosphoric acid, if I have that amount of moles of phosphoric acid, I'll convert it into one of the products. I'm going to convert it into the calcium phosphate. So there's one, that's supposed to be a 1 there. Just going to erase that so you can see it a little bit clearer. If I have 1 mole, we'll change colors here, actually, no, we'll stay the same. 1 mole of calcium phosphate, and there we go, calcium phosphate for every 2 moles of phosphoric acid. For every 2 moles of phosphoric acid. If I have that, when I take 0.022 and I times it by 1 and I multiply, and I divide it by 2, so it's 0.022 times 1 divided by 2, really just dividing it by 2, I get 0.0111 moles of calcium phosphate. So if you have that amount of moles of the calcium phosphate, that could be how much you make if you use all of your phosphoric acid. But as you know, what we need to do is we need to figure out how many moles of calcium phosphate we can make if we use all of the calcium hydroxide. So if we have 0. Actually I'm not even going to do that, I'm going to put it in scientific notation because it's such a small number. If I have 1.96 times 10 to the negative 4 moles of calcium hydroxide, and I convert it into moles of calcium phosphate, moles of calcium phosphate, and I have to convert out of moles of calcium hydroxide, so there's 3 moles here. I got the 2 from here, I'm putting the 3 down here. 3 moles of calcium hydroxide. Then what we get is, let's just take that number, and I have 1.96 times 10 raised to the negative 4. If I divide that by 3, because multiplying this times 1 and dividing by 3 is the same as just dividing it by 3, what I get is 6.53 times 10 to the negative 5 moles of calcium. Got to scroll over a little bit. Calcium phosphate. Hopefully I can, there we go. Oh, yeah, there we go, phosphate. So as you can see, this one is, it never happens because there's just too much of it. Instead, what happens is this one. This is the one that happens. This is my theoretical yield. Alright, this is my theoretical yield, and I'll put a TY over this for my theoretical yield, and I will now label my limiting and excess reactant. This is my limiting reactant. This is my excess reactant. I'll label it up here as well. This is the, I'm going to change this so it's a little bit smaller. This is the excess reactant, and this is my, I'm going to label it down here, limiting reactant. And I'm just going to highlight it so you can see it later when you go back to the answer key. Alright, based on the given amounts of reactants, how much product can you theoretically produce? We found the product of the calcium phosphate, and it says show your work as you calculate the theoretical yield of all products. So now we just have to find the theoretical yield of the other product. So the other product is water. Super easy. Let's do it. So we know the limiting reactant. We have 1 point, let's just make that smaller so we can write more. 1.96 times 10 to the negative 4 moles of calcium hydroxide. When I convert that into moles of water, I have to say that I have 6 moles of water for every 3 moles of calcium hydroxide. For every 3 moles of the calcium hydroxide. So now my equation is a little bit harder in my calculator. I do the 1.96 times 10 raised to the negative 4, and I multiply that number times 6, and I divide it by 3, and therefore I get 3.92. 3.92 times 10 raised to the negative 4th moles of water. Make sure you put down your units just like that. Okay, we go on to the next page. The next page, scrolling over, is 5b. Given the amounts of silver nitrate and cobalt 2 chloride. All right, let's do that. Let's write out a reaction. Silver nitrate is going to be aqueous. You don't have to know that it's aqueous. I'm just telling you that it is. And I'm going to react it with cobalt 2 chloride. That means each chloride is 1 minus, each cobalt is 2 plus. It tells you right here. Each nitrate is 1 minus, each silver is 1 plus. They balance out. These guys need a 2 here. This is aqueous as well. We get a product. We get cobalt nitrate. Excuse me. We get cobalt 2 nitrate, which is aqueous, and we get silver chloride. Silver chloride is a solid. It is a precipitate. Now we have to balance our reaction. There are 2 chlorides here and only 1 chloride here, so we need a 2. There are 2 nitrates here and 2 silvers here, so we're going to need a 2 here. Now our equation is balanced. This is a double replacement precipitation reaction. Everything is aqueous, and then one of the products is solid. If we have 1 molar silver nitrate, so this is 1.00 capital M, that means 1 mole per liter of the silver nitrate. Write out a balanced equation. Okay. If you're given 2.32 times 10 to the second milliliters of the, 2 molar silver nitrate. Okay, so we had a little discrepancy in my question. So that's all right. We'll just change it. So here we go. We'll just make that into 2 molar. So the question stays with what it is. 2 molar. How much do we have? We had 2.32 times 10 to the second milliliters. So that's 0.232 milliliters of this. How many moles is that? We're going to figure out how many moles we have of that. And we're also going to say that we have 1.31 times 10 to the second grams of cobalt. So if we have 1.31, which is actually, that's just 131 grams of this, we're going to figure out how many moles we have of that. I'm going to pause it for 1 second. I'm going to convert this 0.232 milliliters. Excuse me, it is not 0.232 milliliters. It is 232 milliliters. I'm going to convert that into liters. So I take this 232 milliliters right here, and I say, well, if I have 232 milliliters of silver nitrate, then I convert this into liters. If I have 1,000 milliliters and if I have 1 liter, then I will get 0.232 liters of silver nitrate. And then I'm going to say, well, if I have a 2 molar solution, what that means is, molarity means I have moles over liters. I'm going to put my liters over here. I'm going to put moles of silver nitrate here. And I have 2 for every 1. This is an absolute value 1. It's not an estimated number. And now when I do my math, it's going to be 0.464 because I have 2 times 0.232. 0.464 moles of silver nitrate. When I take that, I'll put that in here, 0.464 moles of this. All right, so I have 0.464 moles of this reactant. Now I'm going to convert out of the cobalt 2 chloride grams into moles. So I'm going to take these number of grams, and I'm just going to bring them down here. All right, so I have 131 grams of cobalt 2 chloride. When you find the molar mass of cobalt 2 chloride, you find that it's 130 grams. So if I have 1 mole of cobalt 2 chloride, I have 130 grams. When I do this calculation, I get 1.01 moles of cobalt 2 chloride. So now I take that number, I plug it in right here, 1.01 moles of this reactant. Now it's saying which one's the limiting reactant, which one is the excess reactant. Well, just like we've done in our other problems, we're going to take the amount of moles that we were given, that we calculated through our calculations right there, and we're going to convert them into one of the products. I'm going to convert them into the precipitate. So 0.464 moles. We're going right here. 0.464 moles of silver nitrate. Let's actually just keep this all the same color. So here we go. I'm just going to erase that. So let's go back a few steps. There we go. So if I'm going to keep this green, I'm just going to keep it green. Here we go. There we go. If I have this 0.464 moles of silver nitrate, 0.464 moles of silver nitrate, I'm going to convert that into moles of silver chloride. As you can see here, there's 2 moles of silver chloride for every 2 moles of silver nitrate. Super easy. 2 moles of silver chloride for every 2 moles of silver nitrate. It's the same number. I get 0.464 moles of silver chloride. That could be the amount that I form if I use up all of my silver nitrate. Now we're going to figure out if I use up all the moles of the cobalt 2 chloride. So let's take that number of moles of the cobalt 2 chloride and let's calculate it here. It's in a 2 silver chlorides to 1, 2 to 1 ratio. So my ratio here looks like this. 2 moles of silver chloride for every 1 mole of cobalt 2 chloride. How many moles did I have of cobalt 2 chloride? It's right there. I had, let's continue that down here, I had 1.01 moles of cobalt 2 chloride. And then when you do this math, you have 1.01 times 2, right? What I'll get is 2.02. I'll get 2.02 moles of silver chloride. So now you can see that this one never happens, so you cross it out. This is your theoretical yield. Okay, we can highlight that. And this is your limiting reactant. This is your excess reactant, so we'll label those as well. We'll take our blue pen and we'll say, hey, this is the limiting reactant, this is the excess reactant, and this is your theoretical yield. And you can label it up in the problem too if you want. Alright, so we come up here and we say, yeah, back up here, this was the excess reactant, and this was the limiting reactant. And you can highlight them if you want and show that we figured that out. Alright, we come down here and it says, well, based on the given amounts of the reactants, how much product can you theoretically produce? Same problem as before. We already figured out the one product, we're going to figure out the other product. The other product was sodium, I forget, no, it's cobalt nitrate. Cobalt nitrate. So with our limiting reactant, it's in a 1 to 2 ratio. I make 1 cobalt nitrate for every 2 silver nitrates. I have 0.46 moles of that, so we'll just do that calculation down here before we move on. Let's grab a pen. Let's do it in blue. There we go. So if I had 0.464 moles of the limiting reactant, which was the silver nitrate, and I converted it into the cobalt nitrate, there was 1 mole of cobalt 2 nitrate for every 2 moles of the silver nitrate. And when I do that, I have 0.464 divided by 2. I get 0.232. 0.232, oops, 232 moles of cobalt 2 nitrate. That's my other theoretical yield of my aqueous salt, of a different kind of salt. I come down here, how much of the excess reactant will remain if I have 100% yield? So now I still take my limiting reactant, my 0.464 moles of my silver nitrate, and I convert that into my limiting reactant. My limiting reactant was the cobalt 2 chloride. So moles of cobalt 2 chloride for every mole of silver nitrate. There were two